Okay, so today it's sort of the last topic related to what we have in aerosol mechanics, which is wet deposition. And with wet deposition, we will of course relate it to the theoretical work that we had earlier talked about. Now, what is wet deposition? If we look, take a quick look at the slides. With wet deposition, it's sort of a little more complicated than dry deposition because you have precipitation. So, you really have the fact that you may have precipitation in many forms. So, it can be rain drops in terms of warm rain, it can be hail, it can be snowflakes and so on and so forth, right. So, that complicates it a little bit in that you have a certain phase of the particular precipitation in it, but we essentially won't really get into that. It becomes sort of, so really the steps are the same. The first step is going to be some kind of incorporation of the particle into, and these are called hydrometeors. So, hydrometeor just means we are talking about a cloud drop or a raindrop or a snowflake or a piece of hail, etc., right. So, that's what hydrometeors is. So, incorporation of the particle into it, and that is where our theoretical understanding of particle mechanics comes in. And then something related to deposition rates, deposition velocities, deposition rates of fluxes. And of course, then this deposition rate of flux is now no longer only controlled by the particle, but it is controlled by the rate at which that precipitation is falling, right. So, that becomes a sort of additional complication. So, with this idea, we sort of depict it in this way that you have multiple processes happening, and this is just a slide to show you the complexity of the system. We will simplify it to our usual, in this case sphere, and go with that as the way to go forward, and then link it up to the empirical this thing. But here what is being said is you have, there are 2 or 3 different types of words that are used. One is called scavenging. The scavenging is the incorporation part of it, okay. And so this scavenging really means how did the particle get incorporated. And as is being pointed out with cloud water, you can have this idea that there are again 2 sort of sets of processes. So, you have a set of in cloud processes, and then you have a set of below cloud processes, right. So, you have the certain height and the fall distance and the fall, and of course, I am making very large drops over here. So, you have in cloud processes and what are called below cloud processes. And for all in cloud processes, for all practical purposes, you may assume that the drops are fairly stationary, or they are really not large enough to be falling at any appreciable terminal velocity. And for all below cloud processes, we will be using the terminal velocity of fairly large millimeter sized drops as the velocities that we are looking at, which are going to be the relative velocities between the particle and the drop, okay. So, you have the different processes, and what this is basically saying is you can have nucleation scavenging, which is you have the concept of a cloud condensation nucleus. We will talk about later on in the course Kohler theory and how you will have an incorporation of or a sort of accumulation of water on these nuclei, and that is heterogeneous nucleation. But what is being pointed out is then the drop can evaporate and release particles. So, it really goes in both directions. And again, even below cloud you have the same thing, that you can have scavenging, you can have incorporation of the particle, and then the drop may evaporate. So, you have that also going on, is what is being pointed out. And the third thing that is being pointed out is we are not going to really have a detailed treatment of gaseous pollutants in this course, but gaseous pollutants have a lot of aqueous reactions. In fact, the entire acid rain story, sulfate, nitrate, etc., is driven by cloud phase reactions of SO2 and NOx after the gases partition into cloud drops, right. So, that is another thing that's being pointed out over here. I did used to teach it in a course called atmospheric physics, chemistry and climate in climate studies. I'm looking at whether to revive that course in some form. So, these are sort of the complexities, and then this is of course saying that you have below cloud and then you have in cloud and so on and so forth, and we will treat these processes and try and put a mathematical framework around them. The other sort of thing that is being pointed out over here, and this is just for your information, is that you have really turbulence, things like that happening on millimeter scales. You're really talking of incorporation processes happening on very, very tiny scales. And what is being pointed out over here is, why do we look at micro, meso and all meteorological phenomena, is that the precipitation itself can form because of phenomena that are happening on very large scales, right. So, you have this whole idea of cold fronts and warm fronts meeting and therefore rainfall forming and so on and so forth. So, what it is really saying is, this is one of those processes where you're really accounting across a very large number of scales, is the general idea. Now, in order to start the mathematical treatment of wet deposition, we have to introduce the idea of deposition velocity, deposition flux, just like we did with dry deposition, right. So, we can start with something where we call it below cloud, right, and we say that this is a flux, and we can be talking about it in terms of flux terms. If we are talking about particles in terms of mass, then it is a mass flux over here. In general, we understand that it will be a function of time, and what really is happening is we are talking about this space over here, and we say that I have a concentration in air, and in general it can be a function of z and time of, in this case, particles, right. And because this is a mass concentration. So, this is a gram per meter cube, microgram per meter cubed, etc., etc. And in a lumped parameter approach, I can use this kind of a gamma, which is also a function of z and t, and I call this a scavenging coefficient. And this has the units of inverse time, and I say that this whole thing is operating as the drop is falling, right. So, this is the physical concept, and we can then say, all right, let me neglect the z dependence and just say that, okay, below cloud only as a function of time. I write my scavenging coefficient also as a mean scavenging coefficient, and I say that I start with a particular mass concentration of particles and they keep reducing I can just have a single columnar look at the whole thing. In a column, I start with an initial concentration and it reduces somehow and then gets scavenged out is one way of looking at it. Now, this is what is actually happening in the whole column, right? But at the end of the day, what is it that we want to, one of the things is that, we measure rainfall at the surface, right? Our most convenient measurements of particles of anything happen at the surface, right? So essentially, we want now to define wet deposition as a surface phenomenon, just like we did for dry deposition. So when we move to the surface, we are saying that, hey, let me write it in terms of a wet deposition flux, right? And I write this wet deposition flux. Once again, this flux will have gram per meter square, etc. And I also want to write it in terms of a rain rate, right? So we are used to hearing millimeter per hour. So I'm just going to put it as meter per hour, but I'm going to point out that what kinds of millimeter per hour rain rates are we used to hearing about? We're used to hearing about, very small ones like 0.5 millimeter per hour is a drizzle. And a really heavy, intense, we had 200 millimeters in 5 hours a few weeks ago, right? And so that's like 25 millimeter per hour is really heavy, intense sort of rainfall. And what is this millimeter per hour? It is really a meter cubed per hour falling over an averaged area, right? So all you're doing is measuring meter cubed per hour and saying it fell over a particular area, and that's why I'm calling it a meter per hour or a millimeter per hour. Right, so you want to now say this is a surface phenomenon. I've moved this to the surface, and now I'm going to talk about the concentration in the rainwater, right? And where I'm going to talk about it at the surface. So the rain has done this whole business and has come to z equal to 0. And now it has a particular concentration in it, which is this concentration. And as a function, I can do it as a function of time if I wish, or I can, just say it's an average. So now we end up with a sort of a dichotomy or a problem, right? So this is a gram per meter square per hour. And how am I going to define deposition velocity based on wet deposition flux? This is wet deposition flux, right, at the surface. And it's the same way that I defined dry deposition velocity, right? So then I'm going to define the deposition velocity. I will say Fw, and I can say as a function of time or not as a function of time. And then I will, say it's a deposition velocity which is at the surface. But how did I define dry deposition of particles, etc.? In terms of air, right? So the concentration of the particles in the air, right? So this is where we end up with a problem, in that this is defined with a concentration in air, and this is really in terms of a concentration in the particular form of precipitation, in this case rain, right? So therefore, and when you get into this field, you will find people talking about scavenging coefficient, washout, rain out, all kinds of things, and the terminology will get you entirely confused. And so there is something called a washout ratio. And of course, this will vary from particle size to particle size, this will vary from rain rate to rain rate, etc., etc. But really you need to then say that this is defined in terms of the concentration in rain divided by the concentration in air, and these are all at z equal to 0, because that's where we have measurable, measurement capability. All right. So this is one part of the story, and we leave it here saying that eventually we want to be able to link this scavenging coefficient through precipitation rate to the deposition flux, right. So that's what we're going to do now. And so then we go back to our usual way of understanding objects scavenging particles, or objects intercepting or collecting particles. And what is the object now? It's a raindrop. And what is this object doing? It is falling, and it has millimeter sizes. So it's falling with a terminal velocity. I'm not writing Ts, and I'm putting d because it's a drop, right. And essentially, because it is falling, now we have our streamlines in this direction, right. And basically what we're saying is we have all these mechanisms here, and we have the large particles and the small particles, and the large particles can't get out of the way of the raindrop, but the small particles can easily follow the bending streamline and get out of the way, right. So we can use our same approaches that we used, and so we want eventually to write a single collector efficiency, and now we have to have that in terms of the drop diameter as well as the particle diameter, right. Because earlier we had it in terms of the particle diameter alone, because it was really the particle sort of on its own that was being intercepted. We assume there was a fluid velocity and there was a stationary collector and so on, right. So here now we have to define this single collector efficiency in terms of both the drop diameter and the particle diameter. Let's just go ahead and put all our usual similitude considerations here. Our Reynolds number is going to be in terms of the drop diameter, because the collector is the one that is disturbing the flow, right. And then you will have rho by mu are in any case air properties as usual, right. So we have our Reynolds number, we will have a Schmidt number, but what is our Schmidt number going to be? Our Schmidt number is going to be in terms of the particle diffusivity, right, because it is still the particle that has, if it is a diffusive particle, it has to find a way, from the streamline to the settling drop, right. So here we have our particle diffusivity. Interception, so this is diffusion. The same interception parameter that we had, which now is a particle diameter by a drop diameter, right. And for impaction, we have to define a Stokes number, and that's going to be based, of course, and then we will eventually figure out an approximation where we can say the particle is much smaller than the drop. So we will really, to start with, have a difference in velocity, the relative velocity, assuming that the particle has some kind of terminal settling also, right. And this is the difference that is driving it, and the characteristic length is the drop diameter. And what did we have over here? We had this idea of having a relaxation time, and that relaxation time is going to be that of the particle. It's when the force changes on the particle, how quickly does it get out of the way, right? So it is a rho p dp square cc by 18 mu, and because of this idea, the 2 over there is, to make it a 9 mu, to essentially assume that really it is the half diameter that should be accounted for over here, right? So, I mean, that's what's kind of going on here. So, we have now this, and of course, we can do 2 more things, because you will end up seeing them in, this is some kind of a hydrodynamic correction factor, as we've seen. You've seen a hydrodynamic correction factor as a function of Reynolds number. You've seen it as a function of you've seen it as a function of the solids fraction, which is nothing but inducing a tortuosity in the flow within filters, right? So, some function of Reynolds number, and we'll come to that. And then there is another thing, which is a ratio of mu water by mu air, which for some odd reason is termed omega over here, right? So, with this, we will go ahead and put up our what we know, right? What we know is, we've just finished talking about some of these things, telling you that yes, we have a dichotomy here in that something is in the air, but it has been now concentrated into a falling drop, and we want really to figure out things based on the surface parameters. But this is what we know from aerosol theory, right? Here the Reynolds numbers are large enough for us to be using a high Reynolds number turbulent deposition theory, right? So that is what we use. We know that there's a diffusion limit, we know there's an interception limit. Here of course the collector is the drop which happens to be falling, and we had put this expression up earlier for spheres, but we had considered grasses and things maybe approximately as cylinders, but here we have a sphere, right? And so this is what we had over there in terms of our theoretical number or theoretical expression, both in terms of a Peclet number. So the Peclet to the minus 2/3 is the diffusion term. It had a specific reliance on the Reynolds number, or you could write the Peclet by Reynolds in terms of a Schmidt, right? So whichever way the Reynolds number appears, and the second one is an R square, which is an interception. This is viscosity of water by viscosity of air. I'm coming to the very, okay, here is the very, sort of, this is our empirical expression. I'm going to try and put pointer on here, yes. Oh, what did I do in putting the pointer on? Okay, here we go. So here we have an empirical expression now for this single collector efficiency, similar to our theoretical one, but it has a lot of extra terms and a lot of complications in it. Yet we notice that the first term over there is a Schmidt to the 1/3, but notice that there is a Schmidt in the denominator outside of it. So it becomes a Schmidt to the minus 2/3, right, which is really our dear friend, which is our diffusional Peclet to the minus 2/3, right. So whenever we see our friend Peclet to the minus 2/3, we know that the deposition is happening because of diffusion. And you've seen that, while correcting it, even in the case of dry deposition, we said that that exponent can be anywhere from half to minus half to minus 2/3. So that kind of thing happens over here with the second term and so on and so forth. So you will end up having more terms and a lot of additional things. The second term here has an r on the outside and an r, in one of the terms on the inside, which is an r square, which is equivalent to your interception, right? And so, if you open a book like Seinfeld and Pandis, what you will get is only this, right? And you will get only this, and you will get it at the end of a lot of mathematics, which I am going to just give you a very simplified version of the actual sweep out part. And you may wonder where this came from. And in fact, this is called as a fractional efficiency or something. But this is beautiful aerosol theory, which is to do with the actual mechanisms by which the particle is reaching the collector, right? And so, yeah, and this is where that omega, yeah. So relative magnitudes depends upon the particle size entirely, right? So regardless, so really what you're talking about is which are the particles that are going to be collected by diffusion. You're still talking about nanometer, 10 nanometer, 50 nanometer, etc., are going to be the particles. Whether that's happening in cloud scavenging or below cloud scavenging, that's where you will get the large enough, Schmidt numbers and Peclet numbers for that to happen, right? By the time you move to larger particles, your interception level particles, interception will start happening. So the second term will become important. If those particles happen to be light, then the third term, which has the Stokes number, will not be that important. If those particles also happen to be heavy, then the inertial part will come in. So what is the interception then? The interception is basically this thing that, I have a particle that happens to be riding the streamline, and it happens to be large, but it happens to be light, and so the streamline brings it and it touches, right? And I'll put the idealized case where it touches right here, because we're going to use that in the concept of collision volume, right? So that is the idealized case, that it touches right there. But when will a particle not do that? When it happens to be large and it happens to be heavy, then it just can't move out. So then it's going to inertially impact because the Stokes number became high enough, right? So it's the same conceptualization, except this is happening to a drop, or of a particle and a drop, right? So that's what we have. And in the interception term, only r square. Inertia, if you are in the Stokes term. If you are in the Stokes term. There the r square is just dp by dd. The interception, pure interception is always just to do with the relative sizes of these, and when the streamline comes to dp by 2 of the collector surface, with the assumption that the collector is a perfect sink, and as soon as it touches, it's a perfect sink. So yeah, so we invoke, yes.
So your positions are right, but has there been any fundamental study that may convey that the multiple particles engaging on a large sphere because you have a huge parameter space of Stokes numbers and all numbers.
Yes.
So there has been a fundamental study that looked at regimes and all.
Yeah, I don't know the literature well enough. But yes, I think where one would start would be Slinn, S-L-I-N-N, is the person who has tried to take the pure theory and develop, much of these empirical, expressions, and they are cited in the Seinfeld book, they are cited in all other books. So, you know, that would be one of the places to start, to see what kind of, you know, transfer of information goes from pure theory into the development of these, right? Okay. And then we come up with an interesting finding, which is that now we have the single collector efficiency being plotted, and yes, you have dP, in this case dP by 2 is being plotted on the x-axis, collected particle sizes, and of course you have to specify how it changes when you have the collector diameter change, and that is d, by the way, dd by 2, and that is 0.1 millimeter is the top line, which is you know, fully this thing, the dashed line is 1 millimeter, right? So keep your eye on what's happening here. So you had, in the 1 millimeter case, you had a crossover. So by the time you got to large particle sizes, you ended up having higher, and you can think of it perhaps as impaction efficiency of a single collector went up, right, over and above that of a smaller collector. And how can you kind of justify that, or how can you explain that? You can explain it by essentially saying that you have this impaction efficiency depending on a Stokes number, and the Stokes number is going to have, you know, then going to be related to the fall velocity of the drop, and the fall velocity of the drop is related to the drop diameter squared, right? So it's going up sort of much more with increasing drop diameters, right? So that is sort of an explanation for what's happening here. But I'll ask you an interesting question later on as we move forward. But yeah, let us put this up on the board before we start trying to look at it, which is now how do we move from our understanding of single collector efficiency to a you know, case of what is happening in terms of sweep out, right? So now we come to the real atmosphere, and we say that we have to be thinking of this as a drop that is falling, and in the ideal case you have a little particle here, and the volume that is being swept out by this is a drop diameter plus a particle diameter. The whole thing is getting swept out, right? So you have it getting swept out, and it's let's assume that this is a pi by 4, and you have a drop diameter plus part of, and this is the projected area sort of that's getting swept out. And you know, what is then the rate? The rate over here is going to be a deposition velocity, terminal settling velocity of the drop minus the particle, right? If they were both, you know, having appreciable amounts. And so this is the idea of a collision volume. This is actually the concept of a collision volume in terms of, you know, defining the fact that they are just touching, and that is the sweep, that is the amount of space that a single drop is sweeping out, right? So let's go back to trying to understand this in terms of being able to write what is the rate of removal in this case, let's call it particle mass concentration, right, by a collection of drops. Of falling drops, right, and for some reason this is termed W below cloud, right, and for now we will write it in terms of dP, right. So, since this is going to be mass concentration removal, let's start with the collection of drops. So, I am going to put a wall here and write this expression for you sort of backwards, right. I can assume that I have a collection of drops. I should actually write this as an N. And this is going to be the total number concentration of a set of drops, the drops going from a particular size from DD to, and I am not going to say DD plus DDD, that's a lot of DDs, okay. So, I am not going to repeatedly say that, right. So, this is in some case, the total number of drops here, and what is sort of a, let us say, sweep out in the concept of cleaning out the atmosphere, right. So, we will take this particular expression and say that, I say, all right, it's sweeping out this area, and then of course, unfortunately or fortunately, I don't know, I have to also say that this now is a function of the drop diameter, and this now is a function of the particle diameter. So, I write it, properly here, and right. So, this is the amount that is getting swept off by one drop, all the drops. And what really is getting swept completely clean? We had the eta r times that, in this case, this is the cross section, right? Similar to what we had done in terms of a flow analogy before. So, this is nothing but, this is the sort of distance that is getting swept completely clean of particle mass by each drop, by all the drops, right? Right? And just to then integrate it over all drops, I go ahead and integrate it, and this is over the drops going from 0 to infinity, right? But I haven't yet accounted for this. And how am I going to account for this? I am merely going to say, hey, I have a particular mass size distribution of particles. This I understand very well, right? Because this single collector efficiency needs me to specify this, right? And for the moment, I am not putting this inside an integral. So, therefore, this W. So, now tell me what are the units of everything. This is number per meter cubed of drops, right? And this whole thing then is going to be a certain meter cubed of air, let us say per hour, that is actually swept clean. Swept clean because I have this here. If I did not have the E over there, it would be a meter cubed of air swept out, but not swept clean, right? Because I have the E over there, it is what is totally swept clean, and that's the total, particles removed, right? So then this I have, and what is this? This is a gram per meter cubed of particles. Is that right? In the air, yes, in the air. So these two together is what gives me the hour inverse, which is what I was trying to get to, right? The original scavenging coefficient. All of this together gives me the scavenging coefficient, and did that, well, yeah, that's trying to say it, but I think if we put it up, then we get a better idea of what that slide is saying. But that slide is essentially trying to say this, that, and then we go ahead and make two simplifying assumptions to, make our lives easy. And we say that I can neglect the terminal settling velocity. I mean, really, you're talking about millimeter size and millimeter to several millimeter size drops, and we're talking about micron to submicron particles. So you're already talking about a 10 to the 3, and then in settling velocity you'll have a d square. So you're talking about a 10 to the 6 difference in the settling velocities between the particles and the drops. So this is an approximation that drops settle faster, much faster. So I can essentially put neglect the terminal settling velocity, and the second thing is that the particles are much smaller, so I can write this only in terms of the drop diameter. So if I go ahead and do that, then I just get a cleaner looking expression, and so then I can say that this scavenging coefficient then is a function of dP, and that is what is being shown over there, but that simplifies quite easily to this is still a function of dP, right? And because this is integrated over all the droplet sizes, I haven't integrated it over all the particle sizes, but this is integrated over all the droplet sizes, right? And so therefore this is only a function of dP, and this is a scavenging coefficient, and this has the units of hour inverse. Now I want to multiply it by rain rate in some form, etc., etc. But does this scavenging coefficient look like it bears some relationship to rain rate, or can I write it in terms of rain rate? What can I think of rain rate as?
So that lambda is different from this lambda, right? Because when you multiply by nm,
With? No. The nm is, this is a w. This is a removal rate of particles, right? And this is, this whole thing is the lambda. Wait, no, I don't have the particles over there. Oh, did I? Huh? No. No, the WBC is the below one. The top one is only this thing, but here I wanted to start with the WBC to essentially, say that, we go ahead and then have this, but you can go the other way around also. You can, start with looking at this first, right? Now, how does this relate to rain rate, people? What is the rain rate? I think of all the drops falling and add up over all of them. Right, right. So, all you have is a pi by 6 and this is a dd cubed, right? That is this, and then I have a velocity, and I have the velocity of course of each drop, and then I go ahead and sum it overall drops, right? And this is nothing but my rain rate. And you will end up with a meter per hour over here for rain rate, right? So, this is what I get, and so I can go ahead and rewrite my scavenging coefficient in terms of rain rate. Right. Now, this whole thing is just the P naught, and all I have to do is divide this thing by 1 drop diameter and a coefficient, and then I have a neat expression now for scavenging coefficient. Now, I have scavenging coefficient in terms of a rain rate and in terms of our collector efficiency, which is our theoretical understanding of aerosol collection, right? So, that's sort of what we have, and then we can go back and just write that W, and what they do is now say, all right, now I'm going to take this W dc, which is a function of dp, and then I'm going to integrate it over all dp. And now integrated overall dp is equal to 0 to infinity, and all I'm going to get, of course, now I recognize that this is going to be a negative quantity, in that the particles are getting incorporated, therefore getting removed, and therefore I'm going to write this in terms of a scavenging coefficient dp, and the only term that's missing over there is my particle size distribution, right? So, this is finally where we end up, and what then is this? We end up with the same units over there, which is going to be gram per meter cubed per hour. It's a rate of removal, right? But after going through all this, for some sort of odd reason, instead of writing it in this way, the text, which is Seinfeld and Pandis, essentially end up calling this thing a mass of aerosol change per unit time and all that, which is suddenly you have a new terminology appearing in the middle, which, well. So, this is the story, and we have a nice way of knowing that what people use as scavenging coefficients, and you just find values of them and tables of them and so on and so forth, has a neat link to aerosol theory, right? And that you can then go ahead and get wet deposition fluxes, deposition mass deposition rates, and so on and so forth, right? Okay, that's the wet deposition story, guys, and that brings us to the end of aerosol mechanics in terms of what I had planned. There are many beautiful examples that apply to many different conditions. I think you are interested in many cases where aerosols are removed at walls and so on and so forth. But you know, there's many special cases. You have now all the tools to be able to take them and apply them to surfaces where particles are, that are sinks for particles in some way or another, right? So, we're finished with mechanics, and if there's any questions, I think we have maybe, all right, so all of this is written over there. This is kind of an interesting thing, and this is the question I was going to leave you with. Now, if you plot your scavenging coefficient here as a function of particle diameter, and you have the same two drop diameters, which was a 0.2 millimeters and a 2 millimeters that you had in the single collector efficiency figure. Now your lines don't cross over. Why? You want to take some time thinking about it? We can discuss it on Friday. Yes.
That is common for both, right?
A good question. That's where the issue is. That's where the issue is.
Something constant.
No. The only thing that agrees between that one and this one is the diameters.
The product of the size and the
Correct. Yeah.
So this is per droplet. This is per droplet. So per droplet, but scavenging the coefficient takes care of the entire cloud. So you have more clouds of small particles.
That's exactly it. That this is for a fixed rain rate, right? The same rain rate applies to this curve and this curve, right? So, the previous thing that we looked at was a single collector efficiency, that is per drop. Now, a given rain rate applying to much smaller drops is many more drops, right? And while here it's applying to larger drops is many less drops, and therefore that separation, you know, kind of goes away. Per drop, if you look at it, each larger drop is going to collect a lot more big particles, right? But here you have so many fewer big drops, and that's what's making the change. Okay. Very nice. So, you want to have a little bit of a discussion here? Yeah, so this is a good thing, and in many cases, you know, you can try to do this, which is go back and do a quick calculation with the simplest theoretical form. Take a single mechanism, go do a theoretical calculation about a deposition rate, and go ahead and do the same thing with the corresponding term of the semi-empirical expression, and see how well they agree, right? So, you might want to do it for one or two cases. You go to the pure theory case, right? For example, if you wanted to do that here, you would go to something like this for pure diffusion, right? You know what x is in terms of Reynolds, Peclet number, etc., and you can calculate for yourself some sort of a, in this case, this is going to be a deposition velocity equivalent, right, a wet deposition velocity equivalent. We had put up a WR kind of thing. Then you can go to something like this, the first term, right, and see how you could incorporate something like this and calculate the same sort of value and see whether the values agree or don't agree, right. So, something like that you can think in terms of. Yeah, so I think we can, leave these questions for you all to think about. And let's go ahead and start introducing light scattering, because it's a complete shift of thinking. I know that Prakhar, you should be very interested, because we are going to be talking about aerosol light scattering and what properties and so on and so forth. And today we will just start with a general sort of introduction and maybe not get too deep into it and leave it there and take it forward on Friday. Is that okay? Showing up? Very nice. Okay. Who else has any interest in light scattering? You do? Of the flow itself. Yes. Yes. I see, yes. It is an inverse problem. It is definitely an inverse problem to either make light scattering measurements as a function of either angle or as a function of wavelength and be able to infer particle properties, but you are more interested in tracking the flow. Right. Why are you interested in particle properties? Okay, right. So, we can continue the lecture? Yeah, all right. So, let's take a look at aerosol light scattering. And light scattering is extremely powerful, both in terms of measurements as well as in terms of a method of, as he pointed out, not just aerosol measurement, but in this case for tracking flows, and then perhaps and all sorts of different kinds of measurements, including, for example, this idea of inverse problems is applied all the way to satellite based detectors that then are detecting not just particles, but also the properties of the atmosphere. So, once you have multi-wavelength or multi-angle measurements, how to infer some columnar properties of those particles or of the scattering constituents themselves. So, that is a big field of investigation. So, that, as well as of course in radiation transfer in the atmosphere, in absorption and scattering of solar radiation, and therefore, whether we are talking about the driving of heat waves, whether we are talking about, there is also this whole geoengineering concept that if we are pumping in CO2 and warming the atmosphere, can we go and pump in some scattering particles in the stratosphere and hope that they are going to then reflect some of the incoming solar radiation and therefore save us. But as it happens, when we do that, we have the danger of disturbing the global hydrological cycle in very significant ways, and we have not understood what all those changes will be. So, we are not just going to have a reflection of that, but we may end up having other things. So, lots of implications. Let us start with just saying that with light scattering, we can be talking about electromagnetic radiation. I think a lot of this is probably known to all of you. but I think it's a good idea just to review the minimum number of things that we have to keep in our heads while going forward. So all of us are aware that electromagnetic radiation is really to do with the interaction between electrical fields and magnetic fields, and that's what solar radiation is. And we just want to say that there's different characteristics of it. The characteristics are amplitude, which is to do with really the height of the wave, and that amplitude then links to the intensity of radiation, right? Then there is frequency and wavelength, and of course we know the relationship between frequency, wavelength and the speed of transmission, right? There is also these ideas of phase and polarization. So in fact, when you're looking at something like this depiction of the wave over there, think of it as a three-dimensional thing. So you really have the blue in all directions. So it's really sort of this sine wave, but in 3D. Unless we slice a part of it and only show what is shown over there, and that's this whole idea of polarization, right? So you have this idea of polarization, and then you also have this idea of phase, which is because, starting from some initial point, where are you in the sine wave, if you would, during transmission? And the idea of phase becomes very important because sometimes scattered radiation will not be in the same phase as incident radiation, and then phase becomes very important in either the constructive or destructive interference of waves as they go along. So that is really, all we kind of need to remind ourselves as we move forward, and then we start looking at the many different things that particles do. So when particles interfere with or interact with radiation, we can really think about it in two forms, one called scattering and the other called absorption. And in this ideal idea of elastic scattering, we're saying that energy is received by the particle, it's re-radiated in all directions, and we will talk about the mathematical framework of understanding it, but it's re-radiated in all directions around it. So really, if you're looking at something like this with a particle, and it doesn't have to be spherical, so I'm putting a non-spherical particle over here, and suppose you really have a plane wave of light approaching it. What we're really saying is you have the scattering going off in all directions around it in 3 dimensions, and then we have to understand what is the energy that is being scattered in all of these directions in spheres that exist all around this particle, and relate that to particle properties and understand how to move forward. Now this scattering here, if it happens to be elastic, then the scattered radiation will have exactly the same wavelength as the incident radiation, right? In terms of absorption, the radiant energy gets translated into thermal energy, and therefore you're necessarily going to have a shift in wavelength. So you will have more energetic radiation, the shorter wavelength, then some of it getting used up as thermal, and the rest of it, therefore you will have longer wavelength emission than the incident radiation, right? And then we have this concept that extinction is the combination of scattering and absorption, so a certain additivity. We also have quasi-elastic and inelastic scattering, and so quasi-elastic, inelastic scattering, we have slight shifts in radiation. You're also aware of a Raman effect, where essentially because of an energetic state in a molecule where temporary state, and it relaxes to its original state, the photons that are emitted have a slightly different wavelength than the incident photons, and that can be used to infer the structure of the molecule through what is called Raman spectroscopy. So yes, this is very complex. Of course, we have to simplify it. We will talk about concepts, but I think let's go through some definitions. And here the first is, of course, we are going to be concerned with what is the intensity of radiation, and it's watts per meter square, joule per second per meter square, and that is when we are talking about here it is being shown as incident radiation, therefore you have an I sub 0. We'll really talk carefully about the concept of a scattering cross section, which has the units of meter square, and what it is conceptually we'll talk about later. And we have the scattered energy in watts then being equal to the incident intensity times the scattering cross section, right? And so then that is a watts, which is nothing but a joule per second, and that energy is going away from the particle and you can measure it at various points away from the particle at different r distances away, and that is what we will develop. So what this is saying is we have a scattering cross section, and we have see, this is also a field where if you start reading terminology, people may call it coefficient sometimes, etc., etc. So I think to keep terminology extremely clear, a scattering cross section, absorbing cross section, extinction cross section will always have meter square units. When we're talking about either an efficiency, which is the dimensionless scattering efficiency, is divided, the scattering coefficient divided by some kind of a physical measure of the particle itself. In this case, it's projected area perpendicular to the direction of radiation, right? And we do want to say at this point that indeed, just like we were talking about a tiny fiber being able to take up a lot of diffusive particles, and therefore an eta r can be greater than 1. Similar to that concept, a highly scattering particle, and that depends upon what, we'll just put that up, can in fact scatter so much that your scattering cross section is much larger than the physical extent of the particle. So do not be thinking about scattering cross section and so on as a particle sitting there and punching out this much from a plane wave, right? That is an old class 9 concept. Time for us to get beyond that. I'm sure many of you probably already have conceptually a pretty good idea, but yeah. So what does particle light scattering depend upon, right? So definitely size of the particle. Then we have refractive index. right? And we have the wavelength of the radiation. So, you know, these are sort of very important characteristics, and we can also of course talk about shape of the particles, though in and you know, different sized shaped particles like dust particles are going to scatter very differently from spherical particles and so on and so forth. So, it has very important, and fractals are going to scatter very differently, absorb very differently than single spherical particles. So, it has a lot of practical implications, right, but for practical purposes we will, you know, use spherical particle approximation. So, let us maybe stop with the first sort of concept that we have here, that we want to have a parameter, some kind of a size parameter, which then you know, allows us to look at different regimes, and we can go ahead and put that up on the slide as well. But really we have a size parameter then, which is pi dp by lambda, where dp is the particle diameter and lambda is the wavelength of the radiation. So, much like we had a Knudsen number concept, of course, there the lambda was the mean free path, we were talking about mechanics, here we are talking about radiation, and so here our lambda is wavelength of the radiation, and this is particle diameter, right. And therefore, we have now, and we will talk about what is called Mie theory, Mie, Debye and Lorentz are all the people that are associated with it. But here, just like regimes that we had earlier for mechanics, we have a Rayleigh regime where the size parameter is much less than 1. So, you are seeing particle sizes, see, by the time you are getting to nanometer type particle sizes, the scattering becomes too negligible to be able to be detectable. So, here you are talking about 10 nanometer or a few nanometer sized particles will still be in the Rayleigh regime. All gas molecules are in the Rayleigh regime, right. And then you are going to larger particles vis-a-vis the wavelength of radiation, and that is the Mie scattering regime, which is the intermediate regime, if you would. And then the geometric regime is what, you know, we are used to from our original introduction to optics, and that is where you have geometric optics, where the size parameter is much larger than 1, you know, of the order of hundreds to thousands. Okay. So, we will stop here and we will you know, pick up on developing this on Friday. Thank you.